Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're gonna talk about rocket test stand. So let's dive right into it. Well, first we have to understand what's the need about it. Well, ideally you would always want to test a rocket in a rocket. But problem is rockets are ludicrously expensive and payloads are also very expensive, and sometimes they are humans where you cannot risk them, you cannot go boom on them. So for fundamental reasons we have to test the system. However, you have to understand rocket may look big, may look complex, they are complex, but if you take their complexity, let's say as a value 100, how much complexity is there in the engine? That would be like 90, and one or two would be in the computation and all that jazz. Like majority of the complexity of the rocket is in the engine, so we have to test this puppy. This is the heart of everything. Everything else is just fuel tanks. So fundamentally this is a very complex aspect which we have to test. Another aspect, it is very high energy, which means it's very destructive. You're talking about flame. Now think of it this way: these rocket engines, when they fire, the launch pad is only exposed to the flames basically for a few seconds. But let's say you bolted it down and fired it continuously. Let's say the engine duration test was 3 minutes. Let's say you want to be safe and you want to test for 4 minutes. 4 minutes of an engine exhaust full force, that's very destructive. That's not gonna burn through things, that's gonna erode things. Basically you can take a mountain and fire that engine exhaust at full force. Over time it's gonna erode it away. It's like remove melting it or burning it, it's just gonna erode it away. The amount of oomph is there. So it is very destructive and it had to be handled carefully. You cannot just like use the same logic as launch pad here, because it's supposed to handle it for much longer time. And full power testing is also critical. Engines, rocket engines are not like car engines where they're like, they have a green zone. All engines most of the time are almost at 100%. Only during max q they used to tone down, and nowadays they tone down when they have what you would call landing sequences. So flat out, most of the time if you design an engine and it's, let's say, capable of 10 tons of thrust, it will be at 10 tons of thrust 100% of its life, flat out. So you have to test it at full capacity. It's like you have an engine and it has to be max rpm all the time while you're testing it. So what is the core aspect of this system? Whenever engineer starts to design this, well, it has to be strong enough to withstand max thrust for max duration. This is very critical aspect, because I specified, like if I give you 1-inch thick concrete which is supposed to handle a rocket exhaust for let's say few seconds while its rocket is leaving the launch pad, it's not that difficult. Some coatings can do that. Like you can easily see that in a launch tower structure they have a ceramic coating to handle that, and sometimes even paint can manage that, especially if the duration is small. But when you're gonna tie this whole puppy down and be like, okay, go full YOLO on that, at that point in time game changes. So it has to be designed much more rigidly, much more oomph has to be placed there so it can withstand it for continuously. Like be mindful, continuously it has to withstand that. It's much more difficult than launch pad, and it has to contain the detonation. Whenever an engineer gets the certification, it's like, okay, build a launch pad flat, or he's not gonna like there might be fire. No, there will be fire, there will be boom events, and this is the maximum megajoules that we are expecting out of it. Design the structure as a bunker so it can withstand it. It's not like a in Apollo project. When we are thinking about, we generally think Saturn V rocket, launch pad, crawlers, all that jazz. Significant amount of money, resources, time was poured into the test stand that we do not think about. It's not glorious. But if these test stands were weak, which were the cases with the early designs, where they're like they built the test stand, they tested it, and it blew apart. So next test stand they built, it was much stronger, still blew up. They pulled it even stronger, then it started to handle. Then it was like, okay, minor damage was happening. So we learned the hard way that you have to build a test stand to go boom. Like there is no like it might go. No, it will go. Design the damn thing to withstand it. So it's very robustly built, like very robustly built, and you have to pay serious amount of time, effort, money, resources just to get this puppy down properly. And if done correctly, you have the luxury of that you can keep testing any engines. Like this is not something that you have to retire. So fundamentally you have to take care of that detonation aspect. Like you're not gonna get a set specification, it might have no, it will go boom, your structures will withstand it. Then local fuel supply. Most of the ludicrously high power rocket systems generally have liquid engines, and liquid engines, they are designed in such a way where fuel flowing is a constant thing. The engines expect constant fuel flow, so you have to figure it out one way or the other. You could have a separate fuel depot, but you have to have a huge plumbing to make sure the engine thinks that there is a propellant tank on top and is giving clean flow. That is very critical. Like there is serious amount of engineering doing just the plumbing aspect. And in some sort of scenario where you have to also figure out flame management, because if you are going like this, That's a million pounds of thrust. You are talking about something that can lift hundreds of tons of material, sometimes thousands of tons of material. That's a weight of a building. Like you can literally fire a building into space if you do that. So how the heck you design that? You have to think about it. Now, another aspect, flame. The flame aspect is so serious, especially because launchpad only few seconds, 30 seconds max. This minutes, multiple minutes, so it has to withstand it for, it's like one is like, small fire truck, another is like, whole fire station. So this puppy is fire station. And then just add hundreds and millions of sensor, as much sensor as you can add, and then that creates another problem. Somehow you have to use this sensitive sensors in a place where sensitive things do not last. So there is a whole different level of engineering that people have to just do just for the goddamn sensors, so camera lens don't blow up. So another aspect, like it's completely different thinking. It's like very non-glamorous but very critical core aspect of any space agency. Now we do horizontal testing. Benefit of this system is it can be used for liquid, but it loves to be used for solids. The reason for that is if you have a solid boosters, you don't have to worry about fuel system. Let's say you want to test SRBs, solid rocket booster used for SLS mission. It already has the system. Everything about it is already self-contained, so you just lay it down. Benefit, you don't have to do flame diversion. Benefit, you don't have to do sound suppression. Flat out is like done. Awesome. So this is super awesome. It is easy to construct because bolting down something parallelly to the ground is much easier than, like, you have a small clamping area. You have to just like hold it together like that, rather than like, clamping it out. It has multiple clamps. One of the clamp is strong enough to hold this puppy at full force, but they have multiple in case of rust, bad maintenance, boom bam boom events. It will still hold its load. So it is very easy to construct. Maintenance also, and like in some of the scenarios, when they actually assemble the rocket in the same launch location, and they have like a moving tracks. You can easily pay attention. There are tracks are not for the moving the SRBs. The tracks are moving the coverage around it. So it's like basically there is a shed that protects everything, and then they move the shed around. It's like, so it's much cheaper, and much, even with liquid, the plumbing becomes much more complicated, but if, especially for small engines, that's not a big deal. So this horizontal is a very good fundamental testing ground, and for SRBs they are necessary. Now vertical is something that you want to do. If you can afford to do it, you will do it, because again, liquid flow likes this idea, and not to mention this is the final configuration of the system. So if you design a rocket engine and you are testing like this, yes, still many times we don't think about this, but let's say car engineers, many times they do cost cutting savings where they are like assuming things. Okay, liquid will always go down. Why they are assuming it will always go down? Because they are expecting your four wheels will be stuck to the ground. Same happens with rocket. Yeah, every engineer who's designing, they're assuming everything will go down. And even when rocket is like, looks after launch is directly going perpendicular, it still has enough thrust through from its point of reference is still going up. So every aspect of the engine has been designed in that way, that it's like every directionality is directly from top to down, like from nose of the rocket to basically its engine. So fundamentally, to test that dynamic aspect of it, it has to work. To change the test the hydraulic system, it has to work in that directionality. And then specifically if you are using cryogenic, do you know how to handle ice? Because you could have a scenario where you built an awesome rocket, you tested the engine in horizontal configuration, everything is awesome, but vibration, all they did is like shook the ice loose and then it fell parallel to the rocket, no damage done. But when you have a tall rocket, there was like serious consideration done with Saturn V, where those ice chunks, they were very big, powerful, and if they fall on wrong things, they could cause serious damage. So you will only find those sort of issues when you are doing vertical testing. And turbo pumps love this configuration. It's designed for that. It's like that's its final goal. And launch orientation testing is directly in this. Like if your engine is supposed to work in this way, you will try to test it in this way. And clamp design is also figured out here. Clamp designs are very critical, kind of dull part, but you have to understand it. Every rocket launch pad clamps are designed in such a way that it can hold the rocket at full power. Let that sink in. A rocket is going YOLO and the clamp is like no. So, and it has to be that way. So imagine it this way: Saturn V, you'll not clamp that puppy down. The engine will not start all at one go, but you are talking about 1 million pounds of thrust if only one engine works. So 1 million pounds of thrust, clamp is like, I got this. Then the computer will be like, okay, one engine is working, I'm getting the thrust vector, okay, go to second engine, fire, 2 million pounds of thrust. Engine is like, I got this. Clamp is like, I got this, bro. 3, 4, 5, and then the computer will check the whole system and then give the green signal. And if it fails, it will do a shutdown. And clamp still has to manage it. So clamp at full system, it has to have the ability to hold the rocket for basically indefinitely, so to say. So that's why this testing stand is not just for the engine, it also helps to figure out how the heck you're going to design the clamp, because worst case scenario would be everything is green and your clamp does not detach because you made it too strong. So that is very critical. So we do not think about it. It's like, but understand, like if you watch slow motion footage of space shuttle, you can easily see one engine firing, second engine firing, third engine firing, and at this time solid boosters are continuously firing, and somehow clamps are like, I got this, I got this, computer, check, take your time, check everything, only then I'll let you go. So clamp has to be designed that way. That is very, like, that's why they use explosive bolts. No failure risk. They cannot take hydraulic systems, like, if it fails or something like that. Nope. And bolts have explosive bolts on top of them, so there is no fail probability there. So if they want to hold the rocket, they can hold the rocket. If they want to let go of the rocket, they can let go of the rocket. These things are very abundant when you are figuring out vertical orientation. So even if you are a small rocket owners and all that jazz, you will test as much possible in horizontal, but the final testing you will try to do in vertical. Now, in recent times, as in like current world around 2015 to 2020, a lot of small rocket companies are coming into the market. But here's the deal: most of them do not have, like, deep bank accounts of Jeff Bezos, so they can't buy a area and be like, this is my permanent testing installation. They cannot do that. So most of the time, mobile test stands have been created. Now the idea with mobile test stand is like small rockets equals small engine, small engines equals you can fit almost all of it in a container ship, which suborbital is doing. Copenhagen suborbital is doing. It's quite amazing work. They design the whole system so it can be inside a container ship. So all they have to do is go to an area which is rentable for that day, and they just test it there, which is awesome. Rather than be like, okay, and even if let's say you want to book very far in advance, it will be very expensive. They could be like, they literally be like, okay, we want to test in September. Okay, in September, what options are available? What are cheap options? And if they are like, hey dude, that area is cheaper, it's just a container ship, they have to carry it there. So that is why small scale testing is also becoming much more prevalent. And it's like, renting is expensive, you do not think about it. It's like Boca Chica is not an area that is just like lol. This still is a serious amount of investment that SpaceX is doing in that plot of land itself, and every time they want to do something very complicated, they have to shut down that area. So this is a very serious investment that we do not think about. It's like, rocket, we think about engine, fuel and all that jazz. No, that testing area is a very significant cost. So for that reason, small scale testing system is becoming much more prevalent, specifically with small satellite launch vehicles. And it's enough for small vehicle. Like, again, that shall not test Saturn V F1 engine in this puppy, but it's more than enough. So this was my presentation on a neglected kind of part of rocketry. I hope you liked it, learned from it. In this case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me your disappointment. Please please write a comment, because I try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.